I have completed this first part, basics, the basic signals, the impulse, step, ramp, all the signals, and the classification of signals and classification of systems. I have completed the first part, basics, the first chapter. Now I am going to start the next chapter, which is linear time invariant system, LTI system. I have explained the types of systems: linear, nonlinear, causal, non-causal, time invariant, time variant, all these types of systems. I have already explained them. Now my interest is only this, linear and time invariant. So here the system is linear and time invariant. Okay. This is my interest. So linear means it has to satisfy two properties. One is homogeneity and superposition. Now time invariant. If you apply a delay in the input, let's say a T naught amount of delay, then the output also should be delayed by same amount by T minus T naught, right? This time invariant. My interest is the system should satisfy both this linearity and time invariant properties. Okay. So what is homogeneity? X of t, y of t. It is the system. If I multiply with some alpha x of t, then output also should multiplied with alpha y of t. What is superposition? X of t, y of t. This is the system. If I apply x1 of t as the input to the system, let's say y1t, x2t is applied to the system, let us say y2t is the output. Then I will apply x1t plus x2t as a input. Then the same system. Then if I get, let us say y3t equal to y1t plus y2t, then the system obeys superposition principle. Okay. Now LTI system. Let's say this is the system. Let us say this is the system. Yes. First I will apply a signal which is del t, an impulse signal. I am applying del t as an input to the system. I am assuming that the system output is, let us say, HT. This is the output, right? And I am assuming that the system is LTI. Okay. Now, what I will do is, for the same system is, for the same system, this is the input del of t. I will apply a delay in the input, right? Let us say t minus tau. Okay, this is the delay. This tau is the delay. Now, because it is a LTI system, LTI, linear time invariant. So time invariant. So output also should be delayed by same amount because it is a linear time invariant system. This is h of t and it must be delayed by same amount h of t minus tau. Okay, because it is a time invariant system. Next for the same system, yes, what I do, this is del of t minus tau. This is h of t minus tau. Now what I do is I will multiply this input with x of tau. X of tau is some constant like alpha times input. Okay, so this is the input, this is alpha into input. Then because this is a linear system, it must obey the homogeneity principle. If the input, this is the input is multiplied by some alpha, output also multiplied by the same alpha. That is alpha is here x tau. Okay. Now what I will do is the same system is here the input is x of tau del of t minus tau. Output also x of tau h of t minus tau. Now what I do is I will integrate them. I will integrate this whole input minus infinity to plus infinity, tau equal to minus infinity plus infinity d tau. Then what is the output? Because this integration is a linear operator, because the system also linear system, the linear operator preserves at the output. So output also tau equal to minus infinity to plus infinity d tau. Okay. If you want, we'll explain clearly. Suppose integration is nothing but summation of continuous time signals. Okay. If the signals are continuous, we have to integrate to add them. If the signals are discrete, then you have to sum them. So how to, suppose if tau is discrete, how to write them? Tau equal to minus infinity plus infinity. Tau is discrete. Okay. Tau equal to tau 1, tau 2, tau 3, tau 4, like that. I will take, let's say, x of tau 1 into del of t minus tau 1. Integration is nothing but summation tau respect to tau, so tau limits plus x of tau 2 del of t minus tau 2 plus x of tau 3 del of t minus tau 3 plus and so on, plus and so on. Integration is nothing but summation of continuous time signals. Okay, so I will apply this to the same system. Yes, LTI. We already know that from the superposition principle, we'll get the output as if this is the input, right? Del of t x of tau into del of t, this is the input, x of tau into del of t minus tau, this is the output, x of tau into h of t minus tau. So if you add some of these signals at the input, this is sum, this is sum, this is and so on, what you get at the output? The output, you get x of tau 1, this is the constant, let's say some alpha 1, h of t minus tau 1 plus x of tau 2 h of t minus tau 2 plus x of tau 3 h of t minus tau 3 plus and so on. Because this is the linear system, it has to obey superposition also. This is nothing but superposition. Okay, let us say this is y1, let us say this is y2, this is y3 and so on, right? Let us say this total is x1, this total is some x2, this total is some x3. Okay, so this obeys superposition because it is a linear time invariant system. So this is nothing but, this is a discrete case. If tau is continuous case, this we have to integrate. Here, this is discrete case with the output. If it is continuous case, we have to do this, right? So what I got, this is the system as LTI. I am applying at the input x of tau del t minus tau d tau integral of tau equal to minus infinity plus infinity. What I got at the output? The output I got integral of tau equal to minus infinity to plus infinity x of tau h of t minus tau d tau. right? But I have already explained the properties of del of t here. Here, del of t exists when this argument is 0, that is t minus tau equal to 0, that is tau equal to t. Okay? Only at tau equal to t the impulse function exists. Remaining all cases it is 0. That is integral of tau equal to minus infinity plus infinity. In place of tau, you have to put t, this t, x of t into del of t minus tau d tau. This is the property. And x of t is constant with respect to tau. Limits are tau here. So x of t is constant. Integral of tau equal to minus infinity plus infinity del of t minus tau d tau. And what you get, this x of t, this is area under the impulse signal is 1. Okay, so this is nothing but x of t. We are giving x of t as the input, we are getting output this one, x of tau h of t minus tau d tau integration. So that I will write here. This is the system, LTI system. I am giving x of t as the input. I am getting output is integral minus infinity plus infinity x tau h t minus tau d tau. Only if the system is linear time invariant. Okay. So this is x of t. This is any arbitrary signal. This is linear time invariant system. Okay. So if I give any arbitrary signal at the input, the output I can calculate. This is, let us say, y of t. I can calculate from this formula, right? Minus infinity plus infinity x of tau h of t minus tau d tau. Here, what is the unknown thing here? Okay, this unknown thing here, x of tau I already know because x of t. Just change the variable t to tau. That's it. Okay, this is known thing. This one, h of t minus tau. This is unknown. But how to find out this h of t minus tau? Right? I know that for this system, initially this is linear time invariant system. I don't know what is this. First, I will apply del of t to this system. I can generate del of t in the laboratory. Okay. Then I will find out h of t. Initially, I don't know about this system. I just apply del of t at the input. Then I will get h of t. Okay. Here, input is impulse, right? Sometimes output is also called as response. This is response. Response for what? For impulse input. That is why this also called as impulse response. If the input is impulse, then the output is known as impulse response. So if you know the impulse response, you can easily find the output for any arbitrary signal x of t. Okay. So if I give any arbitrary signal x of t, this is system, LTI system. If I give any arbitrary signal x of t as the input, then first what I do is, first I will find out h of t. First I will give del of t as the input to the system, then I will find out h of t, that is impulse response, and then I will find out output for any input, that is integral minus infinity plus infinity. These are tau limits, x tau h t minus tau d tau. Okay. This operation is called convolution, x of t convolution with h of t. So convolution operation defined only for linear time invariant system, right? The same thing I will derive for discrete time signals also. Let us say this is linear time invariant system, LTI system. I will apply del of n as the input. Then I will get, let us say, h of n. Okay, this is impulse response. Input is impulse signal, output is h of n. That is impulse response. Now for the same system, this LTI system, what I do is, this is del of n, this is h of n. I will apply some delay. That is, the delay is some k. I will apply some k units delay. Then output also must be delayed by same k, because it is a time invariant system. Whatever the delay applied at the input, the output must be delayed by same amount, because it is a time invariant system. Next, what I'll do, same steps. In continuous time case, whatever the steps I have written, the same steps I'm going to write. Here I will multiply this input with some xk. Del n minus k is already there. Here h my n minus k is already there. So xk, I multiplied with xk some constant. So because the system is linear system, it must obey the homogeneity condition. So the output also get multiplied by xk. Now I will sum up. Now what I do, the linear time invariant system. So here xk del n minus k there. I will sum this, sum k equal to minus infinity to plus infinity. So summation is a linear operator. Same things. Okay. Here linear operator preserves at the output because it is a linear system. So at the output, sigma k equal to minus infinity to plus infinity xk h n minus k. Right? But what is this? Del n minus k exists. In fact, del n minus k is 1 at n minus k equal to 0. So at n equal to k, that is at k equal to n. So remaining all case, it is 0. Remaining all case, this x of k multiplied by 0 other than k equal to n. So we will get x of n. Okay. This total value is x of n. Only at k equal to n only the signal exists. Substitute k equal to n here, x of n. Remaining all values of k, you will get 0, because del of n minus k exists only at n minus k equal to 0. That is n equal to k equal to n. Right? Now this is LTI system, discrete system. Now I am applying x of n as an input. Now what I am getting at the output, this one, sigma xk hn minus k. Let us say that is yn, sigma k equal to minus infinity to plus infinity xk h n minus k. So this output is for any arbitrary signal xn, right? So here what is unknown here, xk is already known, xk xn both are same, just replace n by k, that's it. So it is known, but here the unknown part is hn minus k. Yes. So how do you know? Same. First I will apply, this is LTI system. Initially I will apply del n here at the input. Just apply del n here, then you will get hn. This is impulse response. you are giving impulse at the input, you are getting a response. That response is output response, that response is impulse response. If I give any input, any arbitrary input at the if I give any arbitrary input x of n, then I will get y of n as sigma k equal to minus infinity plus infinity xk hn minus k. Right? So now I can represent the system with ht, right? So if you know the impulse response, S1. If you know the impulse response, xt convolution with ht. That's it. If you know the impulse response, you can find out the output for any arbitrary signal xt. So the system is characterized by your impulse response. You can characterize your entire system with impulse response. So I will represent this system with ht. Now I will give xt at the input. Now at the output yt equal to this xt convolution with ht if the system is LTI, linear and time invariant. Now suppose it is the continuous time case. Now if it is a discrete time case, hn. Now I will apply any arbitrary input xn, then I will find out yn equal to xn convolution with hn. Right? So this is the concept of convolution. Now so yt equal to xt convolution with ht, it equal to integral of tau equal to minus infinity plus infinity x tau h t minus tau d tau. So what we are doing here actually, suppose xt and ht are already available for me. Okay. Now what I am doing to do this operation, this convolution operation, what I have to do? First I will change the axis x of t to x of tau and h of t to h of tau. Just replace t with tau. The time axis t changed with tau axis. That's it. Now I need this one, h of t minus tau. So first what I do is this, from this h of tau I will apply time reversal. So tau tends to minus tau. Then what you get, h of minus tau here. Okay. Now what I do? Now I will apply, I need this one, h of minus tau plus t. This I can write minus tau minus t, minus of tau minus t, right? Now what I do is this tau change to tau minus t. What I will get, h of minus of, wherever tau is there, replace the tau by tau minus t, tau minus t. Then I will get h of minus tau plus t, right? So this is what I need, h of t minus tau. So after getting these two signals, x of tau and h of t minus tau or h of minus tau plus t, what I am doing here I am doing multiplication, right? X of tau into h of t minus tau, that is x of tau into h of t minus tau. Next I will multiply these two, and then what I do, I will integrate. Integration is nothing but area, tau equal to minus infinity plus infinity. This is area of x of tau into h of t minus tau. This is the output y of t, right? This is what we are doing here. Same operations applicable for discrete time signal also. That I am not explaining here. Now I will explain this concept graphically. Let us say, let us say I have x of t and h of t are available. Let us say this x of t is from t1 to t2. X of t exists from t1 to t2, and h of t exists from t2, t3 to t4. In remaining cases, it is 0. Okay, so impulse response available and x of t input also available. Then I have to do the convolution. So what is convolution? X of t convolution with h of t. That is integral of tau equal to minus infinity to plus infinity x of tau h of t minus tau d tau. This I have to do. So first I will change the axis to tau. X of t is there. I just need to change the axis to tau. Replace t with tau. That's it. This is tau now. This is x of tau. Signal will not change. Because just we are changing the axis, right? So the limits are from t1 to t2 only. t1, t2. Now the next step, what I have to change? H of t also change to h of tau. This is tau, h of tau. H of tau, the shape will not change. The limits t3 to t4. t3, t4. Okay. This x of tau and h of tau. Now I want to do the convolution. So x of tau, and we need to do h of minus tau first, and then we need to shift by small t amounts h of minus tau. This is h of minus tau minus t, right? First we have to shift, first we have to time reversal. First we have to do time reversal of h of tau, that is h of minus tau, right? This is tau, this is h of minus tau. Let us say what we get, h of minus tau. We have to flip the signal about y-axis. So this t4 becomes minus t4, this t3 becomes minus t3. So it's 0. So this t3 will come here. This we have to multiply with minus 3, minus t3. The t4 will come here somewhere, minus t4. Okay. Suppose, for example, if t3 equal to minus 2 and t4 equal to, let us say, 4. So 4 becomes minus 4. This 4 becomes minus 4. This minus 2 becomes plus 2 because minus t3. t3 equal to minus 2, right? Minus of t3. t3 equal to minus 2 becomes So these limits gets multiplied by minus. That's it. This is h of minus tau. And then what I have to do? This one. H of minus tau I got, and then I have to apply a delay tau minus t. This is small t delay. Okay. So if small t is positive, we want to apply h of minus tau minus t. This, right? If t is positive, let us say t equal to plus 2, then h of minus tau minus 2, right? We have to shift right. This h of minus tau, we have to shift right by 2 units. If t equal to minus 2, h of minus tau plus 2, right? We have to shift left. Tau replaced by tau plus 2 means we have to shift the signal h of minus tau by 2 units left, right? These things I have already explained in the previous lectures. So if t is negative, the signal moves towards left. This h of minus tau moves towards left if the t is negative. If t is positive, the signal moves towards right. That is delay. This this left side movement is advance. This right side movement is delay. If t is negative, here t equal to minus 2, h of tau plus 2. H of minus of tau plus 2 means this is advance. If you do advance, the signal moves towards left side. If you do delay, that is t equal to positive here. Here tau minus t. Tau minus 2 means you have to shift this entire signal 2 units by right side. So the signal moves towards right side. I don't know this t, small t. Okay, I need to find out a small t. What is small t here? Y of t equal to integral minus infinity to plus infinity. These are tau limits. X of tau, h of t minus tau. Okay, these t limits I need to find out. If I find out the t limits, then I will find out the y of t, from where to where the signal exists. Okay, the signals are existing from one is t1 to t2 x of t, and another h of t exists from t3 to t4. I need to find out y of t, from where to where the signal exists. Okay, so for that I am using the convolution x of tau. This is h of tau. This is h of minus tau. Then I have to shift by some amount of small t. Okay, this is x of tau. Let's say t1 to t2. Here it is given, and h of minus tau minus t. This I have to represent. H of minus tau is there. This is h of minus tau, and h of minus tau minus t means you have to add small t to the limits, right? Tau minus tau minus t. You have to add this t to the limits of this h of minus tau. Here we have to add t, here we have to add t. That I will write here, the signal. I don't know if we add this small t, I don't know whether signal shift towards positive or a positive side or a negative side. That is towards left side or right side. I'm just writing the signal shape h of minus tau minus t. I'm just writing the shape minus tau plus t, that is here, minus t4 plus t minus t3 plus t. That I will write minus t4 plus t minus t3 plus t. Okay, these are the limits I have written there. Minus t3 plus t minus t4 plus t. This is h of minus 2. So what I have to do next? The next step is this one. We have to multiply these two signals. Okay. So while doing multiplication, we have to know that where this multiplication becomes 0. That is where you get actually 0 if there is no overlap between these two signals. This x of tau and h of t minus tau, these are two signals. If you don't get any overlap between these two signals, then you will get 0, right? Suppose this t, this small t, this small t. So this point, okay, this is the point. Okay, if this point is, let us say, I'll write this signal, this t1, right? If this point exists here, right? This point exists here, that is minus t3 plus t here. Then how will be the signal? This, right? This is the signal. Minus t3 plus t here, and here minus t4 plus t. If exists like this, we are multiplying x of tau and h of t minus tau. Here x of tau is there. Here x of tau is there. Here h of minus tau plus t or h of t minus tau is there. We have to multiply these two signals. If I take like this, okay, if I choose this t such that this point will come to here, then is there any overlap between these two signals? This is 1, this is 2. Is there any overlap between these two signals? Okay, there is no overlap because here to here 0, 0 multiplied by anything you will get 0. But here to here the signal is there. But we are multiplying these two, 1 and 2. So multiply these two, you will get 0. And here 0 is there. But here t1 to t2 we have some signal is there. But if you multiply these two, 1 and 2, you will get 0 only. 0 multiplied by anything 0. So in this case, you are getting 0 y of t output. So they are calculating output y of t. Okay. If you choose this t, that is this t, thus that t, this t, that t, this t, both are same. Okay. If you choose that t value such that this minus t3 plus t, this is the point, minus t3 plus t is at this point t1. So this is the point t1. Okay, then there is no overlap. Okay, that is the leftmost point. So I will equate this minus t3 plus t to some t1. That t1. I'm equating this t1. Okay, what you get t equal to t1 plus t3. If we choose this t such that t1 plus t3, what is t1 plus t3 here? What is t1 plus t3? So this is x of t, this is x of t, which has lower limit is t1. This is h of t, which has lower limit is t3. If you choose t such that sum of these lower limits of these two signals, t1 plus t3, that is the leftmost point of y of t output. If you choose this t is less than this t1 plus t3, then you will get 0 overlap, 0 output, because there is no overlap between x of tau and h of t minus tau. Okay, So this is the leftmost. So T1 plus T3. This is the leftmost point. Okay. From this point, you cannot move further left. If you move further left, you will get zero overlap. You will get output is zero. Okay. So that output is zero. That is not my interest. I have to get some non-zero output. So then what I do? After getting this leftmost point, I will move towards the right side. Okay. Then I will get some overlap area. So I will again draw these two signals, h of tau and h of t minus tau. Here. This is tau, this is x of tau, this is h of t minus tau. Okay. Now this is the signal x of tau. This is, let us say, this is t1 to t2 and h of minus tau plus t. Right. We will draw here exactly at this point. This is minus t3 plus t. This minus t4 plus t. This is the signal. Yes, minus t3 plus t minus t4 plus t. If this point is exactly equal to this point. Now there is no overlap. This is this point minus t3 plus t equal to t1. This minus t3 plus t equal to t1. That is t equal to t1 plus t3 is the leftmost point. Okay. We choose t such that t1 plus t3, this is the leftmost point. We choose less than this t1 plus t3. This, if t is less than t1 plus t3, then this leftmost point shift again towards left side, then you won't get any overlap area. Now you have to choose the t such that it has to move towards right side. Now I am moving this signal right side, towards right side. I am choosing the t such that it has to move towards right side. Okay, so I am moving this h of t minus 2 towards left right side. So I want to find out the rightmost point. I don't know in between. Okay, you will get some non-zero values because you will get some overlap area. So suppose I'm shifting this like this. Okay, like this, like this. This is moving towards right side like this. Okay, like this. If you change this t value, this shifting will be towards right side. You take this t value such that it has to move towards the right side. Then you will get some overlap area, right? So I want to find out the rightmost point. From where you will get rightmost point. Okay, so this is h of t minus tau, and here for x of tau, this is the t2. Okay, if of t minus tau, if this signal is exactly at this point, if this point is exactly here, that is this exactly here, then you will get rightmost point. That is, this is minus t4 plus t, this is minus t3 plus t. If you shift further right side, you won't get any overlap area. Only here to here the signal is there x of t, right? You won't get any overlap area h of t minus tau to x of tau. This is x of tau, this is h of t minus tau. You won't get any overlap area if we shift further right. So this is the rightmost point, minus T4 plus T. What is that? This one, T2, right? So minus T4 plus T equal to T2. At T equal to T2 plus T4. This is the rightmost point. Rightmost point of T. Okay. So y of T is integral tau equal to minus infinity plus infinity x of tau h of t minus tau. Y of t exists only between y of t exists only from, so this y of t exists only from this t2 plus t1 plus t3 is the leftmost point of t, and the rightmost point is t2 plus t4. What is t2 plus t4? Right? This is x of tau, this is h of tau, or x of t, h of t. This is x of t, this is h of t. Rightmost point is t2 plus t4, and leftmost point is t1 plus t3. Right? So this is the leftmost point, t1 plus t3, and this is the rightmost point, t2 plus t4. Okay, this is so less than this t1 plus t3, you have y of t equal to 0. Greater than this t2 plus t4, you have y of t equal to 0. So in between you have y of t. Okay, so in between these two values only you will get some overlap between x of tau and h of t minus tau. Okay, you multiply them and you will find out the area of that multiplication. Then you will get y of t. Okay, so y of t exists only from t1 plus t3 to t2 plus t4. Remaining case y of t equal to 0. Similarly, for discrete time case also, suppose y of n equal to x of n convolution with h of n. If x of n exists between n1 less than or equal to n less than or equal to n2, n1 to n2. Suppose the signal is like this, discrete time signal. Okay, suppose this is n1, this is n2, this is x of n, and let us say h of n exists from n3 to n4. Let us say this is n3, this is n4. Then yn exists. This is the convolution of x of n. Yn exists from n1 plus n3 to n2 plus n4. Lower limits, add lower limits, n1 plus n3 to n2 plus n4, add upper limits.